The next time frame of interest is the immediate time frame. Roughly I'm saying 5 minutes, but actually it could be faster than that for AGC, automatic generation control. But at least let's segment off the 5-minute to 24-hour schedule for use of economic dispatch, security constrained economic dispatch, and security constrained unit commitment as implemented in the competitive marketplace, where one has to come up with market offers, that is bid and ask. You have to do this on an energy basis for the daily contract. In the future, I think we'll see hourly energy contracts, just as we've seen the development of an energy imbalance market now in the California and Oregon area to take care of the forecast errors. It's very hard to forecast even 24 hours at times, and therefore you need to rebalance or reschedule. Of course, the other need in this time frame are the commodity hedges. That is the contracts for fuels, electric energy, and ancillary services that are needed to keep the supply chain functioning. So what's the framing? Well, the focus here is going to be on traditional short-term demand forecast. Hourly for the next 7 days or 168 hours. Extendable to immediate. It's applicable to most markets. The same tools can be used for commodities such as fuel, as well as electric energy, and even somewhat to the stock market if you wish to get into that. But what we're really doing is doing pattern analysis and parameter estimation to identify what history tells us will be the driving forces and the actual consumption into the future. What's really missing is econometric forecasting. We are not going to be going down to the level that we will replace all refrigerators for more efficiency, and therefore 20% of the demand is reduced because we have more efficient means of storing our food. We're not going to talk about change of water heaters or changing things from gas to electric or vice versa. We will talk a little bit about the impact of distributed generation, whether it be wind, solar cells, or biofuels and microturbines, which are becoming more and more prevalent throughout the world and the United States at this time. So we're going to sort of barge into that area a little bit, but we're going to do that only to show those drivers, the driving forces that change the demand the most. Energy storage has become the huge concern with the renewable energy contracts of how do you deal with the fact the sun does not shine all day long, only for a certain number of hours during the day and only when there's no clouds. Wind generation is only there when there's wind, which is primarily the morning and evening periods, whereas solar cells are in the middle of the day for the most part. And how do we store this energy? If we have biofuels and we don't have constant production of them, how do we consume them, or how do we store them? And that's what energy storage is about. At this point in time, pumped hydro is still the technology that can store the most energy. It is also, of course, one of the more expensive ones because you have to build 2 reservoirs at Tehachapi or Tom Thumb Mountain or at Ludington, Michigan. You have to build 2 reservoirs or have one that's available for you. In the case of Ludington, it's Lake Michigan is the lower reservoir. On Newfoundland, the island of Newfoundland, the ocean is the lower reservoir. So you start pumping salt water upwards, which has its own characteristic problems. Demand response is another way of energy storage. We can store cold or heat in various containments, such as salt water or earth, and move that energy, the cold or heat, into its used location, such as a shopping mall, a residential home complex, or a high-rise when it is needed. So it's very common, for example, in Portland, Oregon, that the Lloyd Center Mall has a skating rink. It is used to store energy at night, that is cold energy, when it is cheapest to do so, so that during the day the air conditioning compressors do not function at all, do not have to function. So that's a way of changing demand around. This is done extensively in Wisconsin with heat pumps, as they put essentially large garden hoses under the ground, under the frost line, store energy or get energy from the ground to make the heat pumps more efficient. The whole goal here is an economic goal, economies. How do we save demand at the peak from being at the peak? How do we move demand from the peak and bring it back during the off-peak periods? Now, if all we're doing is moving demand away from the peak, we of course are reducing the overall energy required. If we're moving from one period of time to another, the amount of energy that we need is going to be a little bit larger because of the inefficiencies of storage, even if they're very small, like 3 or 5%. So what is demand? Okay, again, the demand we're trying to forecast here is the demand at the consumer's point of delivery. It is not including the load and losses typically of the transmission system. It may include some of the losses at the distribution system if that is where our telemetry or sensors are for the power demand for that group of customers. With smart meters, we of course can meter exactly where the command interface is between the provider of electricity, the supplier, and the buyer, the customer of the electricity. Smart meters move it all the way down to there. And of course, that's when we get our most granularity. And being able to forecast at the meter level is going to be more interesting than forecasting at the distribution feeder level and within the substation. So we're not going to forecast losses. These are going to be available once we forecast the demand. We can calculate what the losses should be based upon our power flow technologies. We're not going to forecast ancillary services, but we can extend and include those services in terms of what is needed based upon the demand that is forecast. We could use this for forecasting market prices, clearing prices, and then we start talking about, okay, are we looking at random variables or stochastic processes? And there's a subtle difference between them. Random variables is sort of the first step to including uncertainty. Stochastic processes are another approach to include uncertainty. We will touch on that briefly. Probability. Okay. If something is uncertain, we then should look at the probability. Is demand mostly random? Yes, it is. We don't know what point in time the appliances will turn on or off. We don't know what their weather dependency is that an individual will select. Everybody sets their own thermostats in terms of heating, cooling, and everybody uses TVs or internets or surround sound stereos or whatever, or even in the future electric cars at their own whim and not based upon a offering of when they could use it and what price they would then pay for charging it. So far we're saying demand is mostly random. We don't interface with the customer enough to require them to tell us when they will want the electricity there, and therefore they must pay for it when we provide it. So it's more or less random as far as when they wish to use it. That's how we make them happy. Commercial demand is less random. We have the customer-centered workday. Your cleaning shop is open from 7 to 7, for example. Well, that's when they're working. That's when they're going to be cleaning. That is when they will need the energy to do the cleaning, the ironing, etc. that they get into. If we look at commercial demand for a grocery store, well, is it open 24/7 or is it open only during certain hours of the working day? Well, it doesn't matter when they're open as far as when the coolers and the freezers are working because they must work continuously. However, the extra demand to make the store pleasant for people, the lighting that's required, etc., and our heating is something that's going to be based upon when the facility is open for customers. Industrial demand is almost deterministic. Alcoa is going to make aluminum, and they're going to make it on a shift, first, second, or third shift. Basically, we know we can understand their schedule and get it from them, actually. They're glad to share it within a certain extent because they wish to get the best price possible. Okay, what is a random variable? Well, the easiest way to define a random variable is to take a die and roll it. What is the outcome? One of the numbers shows up out of the 6 sides. Okay, and therefore we know that 1 out of 6 tries, there's a 1/6 probability that a 1 will show up. Now let's think of that as a random variable. Now, how would that be used in forecasting? Well, if we look at the weather forecast, we can come up with a randomness in terms of the weather will be hot, not so hot, and hotter than normal as a way of looking at the weather forecast distribution. Another way is to look at a stochastic process, especially as a Markov type process, where we see a certain pattern of demand over time. Financial markets typically use stochastic processes to model the stock market changes and commodity. They typically get into time series that are mean reverting, arch or garch, and therefore have a certain forecast built into them because of the predictability of what the fundamental price will be based upon econometric factors. So what are the categories of forecasting? Well, qualitative is one. We have experts. The senior operator has always been very good at forecasting typically. And of course, the market analyst is another person who is excellent because this is what they do all their lives. And they have 10 or 20 years of on-the-job training to think about why the demand is at the level it is at. These are called Delphi opinions or the Delphi system. This is one thing we would like to model with neural networks, for example. The quantitative approaches typically are time series based. They use, first of all, linear or nonlinear regression. They do some kind of filtering. They can do FFT or common type filtering, or they could do very simple exponential, double exponential, or Holt-Winters type filtering to tease out the pattern underneath, the parameters for that pattern, and use that for the future with the basic assumption that history will repeat itself. Another approach mathematically is to use an autoregressive moving average or ARIMA model. Now these two were used before state space was really being considered because of what the computers could do. ARMA and ARIMA were very popular when the 7080 and 360 came about, which was roughly the middle 60s, 70s. And as computers became cheaper and more capable, more memory, more disk space, we went into state space representations, the so-called modern control theory approach. ARMA and ARIMA can be converted into a state space model, as well as FFT. Common, of course, filtering is the ultimate state space model. And part of the projects you may select to do over a term of a course is to show how to convert each of these into its equivalent state space model and look at the tool differences you would use. The last thing we'll do is curve fitting by artificial neural networks, ANNs. And as stated before, these are really just nonlinear curve fitting techniques, which have been quite useful. Okay, econometric. What are the economic indicators that we might use to determine what the demand will be? Number one, unemployment. As there's more unemployment, people spend less, and therefore the electric demand decreases. Factories are closed, businesses are closed, and therefore the demand withers and goes away. Not so dramatic is weather changes. Winter is great for electric heating, natural gas furnaces in the colder climates. And summer, when it is hot, of course, is when we use our air conditioner or some other way to make the environment we're in agreeable to work. There's other factors such as sociologic. For example, do people want to do green resources only? And this is when people will start to change their pattern of usage so that they're more in line with the resources they wish to do. This is more behavioral economics and is very interesting unto itself and is a lot of interest in terms of agent-based computational economics. Now, the whole thing about economics is demand for any product, for all products, is a result of a need. This is the cause and effect. Behavioral economics deal with individual spending, especially how do you get somebody to spend money when they could have made a better decision in their own value for that money. For example, why do we buy the more interesting or more exotic car instead of just a car to get us back and forth to work and the grocery store? In industrial mix, why do we shun some factories from opening in our towns as opposed to others? Why do we entice some companies to open factories in our town? And of course, the commercial mix. Do we enable shopping malls, or do we just use strip malls, or do we just use the original small stores in downtown? All of those determine the demand for electric energy in the future. Oh, what are the applications? Well, there's a table in the book. Scheduling, we have to worry about thermaling the schedule units, the on and off times, the startup and shutdown cost, and so on. Hydro, how can we schedule the water? Do we have to worry about navigational flow, enough water flow for boats to get through? Do we have to worry about fish ladders and how those can be controlled so that we have more fish going upstream? Pumped hydro is traditional energy storage that we've talked about. And the new energy storage today, of course, is batteries and flywheels. How do we use those to change the cost, to reduce the cost for our customers? And of course, demand response. How do we give our customers the choice to not use electricity or to use electricity that was stored at a different point in time, sometimes with their own capital investments, which may or may not be aided by us. Other applications are contract negotiations for interchange, for transactive energy, and of course our independent system operators and the traditional power pools did all of this contract manipulation based upon future forecast. The one step ahead forecast, AGC, needs a good prediction of ACE, the area control error, to know what to do in the next 60 minutes. Should we go through a prohibited zone, that is a certain level of generation that the unit cannot stay within? Should we go through the next valve point so we have a valve fully opened and totally open and locked and go on to the next one? How do we use our units so we get the best reliable operation at the least cost? Next 24 hours, we're talking about security assessment, unit energy scheduling, ancillary service markets, the reserves, for example, as well as frequency and governor response, the energy imbalance market. How do we handle the fact that the ISO could not forecast the proper energy for hours 6, 7, and 8 tomorrow, and therefore needs more or has too much energy? What do they do with it? How do we maintain our equipment? What are the maintenance schedules? When can we take a line out of service? When can we take a bus or breaker out of service? When can we isolate a demand or feed it from an alternative feeder so that we can do the proper maintenance? And therefore we have to look at bus demand forecast. The work we'll be doing in this chapter is based upon the component integration into an additive series where we have a base component, a weekly component, a seasonal component, and noise. Seasonal is somewhat misleading. First thing we think of as seasonal is the winter, summer, fall, and of course spring. What happens during those seasons that's unique as we go from, except in the northern climates here, of heating during winter, cooling during summer, and then we have that in-between period where there's more uncertainty as to using one or the other on almost a daily basis. Seasonal can also mean that we repeat the days or the weeks in terms of everybody goes to work Monday through Friday. We have our peak demand typically on Wednesday, and Monday and Friday are normally the startup and shutdown periods for some production. And therefore we see this little hill, if you will, between Monday and Friday. And of course the weekend we're all off. We're not producing a lot, so therefore the energy demand is down. And we're socializing or just gone fishing. The alternative to this is a multiplicative, where we take our different components and instead of adding them, we multiply them. So we think of terms of percentages, or will, of the base load in terms of what is going to be appearing on a weekly or seasonal, and what part is noise. Our path will be additive. That's the path we'll select. Most econometric techniques are additive. They're a little bit easier to understand as we gather so many appliances and have a certain number of them. We start to get into multipliers, of course, because we have so many homes of this size. Therefore, all the appliances are the same. And if we have 100 homes like this, all we need to do is model one home, and we got the demand for 100. So that's kind of a mix between the two. The difference between the two approaches is slight, but there's a strong enough incentive not to get fully into the multiplicative based upon historical success of use. Hourly system demand forecast will take the overall demand and break it into a mean, or an explainable or constant, and an unexplained y hat. And our y hat in one case will be modeled as a function of previous demand over other periods and the noise of other periods, the W. Hourly bus demand forecasts typically used today are simple multipliers of the total system demand. Now, these multipliers may be segmented or categorized by day of week, by hour of day, by type of weather, etc. And here we're starting to get back into the multiplicative world of coming up with a forecast. But this is the way hourly bus demand forecasts are accomplished, typically. What are the interesting extensions? What happens when I shift a feeder from one bus to another? How much of the demand is now on a different bus, and therefore my security analysis is totally changed. So there is impact of forecasting on all of the security, energy, ancillary, energy imbalance, etc. markets that we've talked about previously. And we have to be able to take care of those details. There's also the new interaction between the fuel markets and the electric markets. Remember, electricity is always based upon the use of a fuel, whether it be fossil, wind, solar, or some bio-type fuel. It's always based upon some other resource. One of the interesting things to do with this connection between these two markets, as Enron did very cleverly, is you can turn electricity into gas reserves, just as we can turn electricity into hydro reserves in Canada. What we do is we do not produce those resources, and we use alternative resources instead, and therefore we can get to the original resource we saved at a future date, such as with hydro. The thing to remember about supply chain is the difference between the price of the fuel and the price of electricity is called the spark gap, because it only takes a spark to change the fuel into electric energy, or at least a big explosion, I guess, to be humorous. If we look at all the various futures markets of how we would trend from operational planning to system planning and long-term use, we have the various futures markets to go through of electric, natural gas, oil, coal, nuclear, note here, hydro, and of course, demand. All of those future markets are there. And the need for a demand market is becoming quite clear, so that when we build a new subdivision and get another chunk of demand for electricity, we can control when it occurs, so we have time to properly build and analyze how that demand will impact the security of the overall system. So dependency. Electricity is dependent. It's primarily a function of the fuel cost. The coordination is critical for many contracts and therefore the cost of production and storage. Hydrothermal coordination is a key financial factor. Take or pay fuel contracts or other specialized fuel contracts are critically important to those companies that use natural gas from the wellheads. Market contracts are center in a competitive market, such as any of the independent system operators or competitive markets around the world, where we must do hedging, or we're going to do trading on spot and future markets and convert one to the other. Converting electricity to fuel gas for storage, or converting electricity to water that's then stored, is the market contracts that are going to be of interest. And of course, longer term fuel contracts. As the price of oil changes and the price of gas changes, we want to get into longer term contracts, either to make our costs lower or to split the difference with the wellhead in terms of what is the price going to be. Transactive energy contracts is a new endeavor to enable the customer to directly buy the energy they need when they best wish to afford it. So they may decide to change their energy use through energy storage devices to reduce their cost. And of course, there's always other technological chances to be concerned about. Wind and solar cells are a major technological advance that require revamping of the way things work, of the computers we need and how they're interconnected, and the rules we use to balance the instantaneous production of electric energy and its consumption, as well as the biofuel type or the microturbine type natural gas plants that are being sold heavily throughout the world, even in the United States. Okay, what are the forecasting basics? Well, the techniques are really quite similar. There's not a whole lot of difference between them other than the math of generating the parameters and the math of determining how much of each component should be applied by a specific technique. Market prices and quantity forecasting uses similar. Hydro inflows uses similar tools because we have to know how much water is coming into the drainage system that forms up a hydro reservoir. There we have to look at snowpack, how much snow is there, how hot is it, how quickly is that snow going to melt, how much rain is there a monsoon that's going to feed this large hydro reservoir or not? And of course, the one that's interesting to me is competitors. How are competitors going to bid to provide the same service, the same electric energy, the same ancillary services, and so on? Regulatory issues, of course, are key and forefront in terms of deciding what resources do we develop. What should the rates be? What will the long-term rates be? Will be because we want to develop something today that we can use for the next 20, 30. And in the past, we've always gone out to 50 years. Does that still make sense now with solar cells? That is changing about every couple of years and becoming more efficient. So we have to look at the pollution cost. Are we going to have new regulations requiring pollution markets, as announced that China is going to implement? And how is all of this driven by new technologies? Solar cells, wind generators, biofuel microturbines, and how are the appliances going to improve their efficiencies and therefore reduce the electric demand? Some of the original methods for forecasting include smoothing, like exponential or double exponential, or the Holt-Winter techniques. These are very early control type algorithms before computers became too powerful, even when we're using analog computers, is we use this kind of smoothing to be able to forecast the future demand. Some very widely used filters such as general adaptive filter, GAF filter. Regression analysis is something that everybody has been exposed to, not just for forecasting, but also for modeling devices and systems. We can do linear or nonlinear regression. We can do multiple regression because it's in addition to the basic time series, there might be certain economic factors we wish to separate out or weather variables we wish to separate out to fine-tune the number of components and the accuracy of the forecast. Again, the key here is to be parsimonious, to be cost-effective and efficient with how much is done. We can use logistic regression, discriminant analysis, multivariate analysis of variance, and factor analysis. So we've gone all the way from control, our programmable logic controller basis with smoothing, regression being basic econometric, and then multiple and logistic regression being advanced econometric type techniques. In economics, there's many different tools we can use. One of the pattern recognition tools is cluster analysis. How do people flock and use the same products at a given point in time? Multidimensional scaling, correspondence analysis, conjoint analysis, canonical correlation, structural equation modeling. Okay, here we're getting into pattern recognition. How do we keep up with the joins as our neighbors? How do we follow the market bids we receive? And finally, we get down to the fact we're getting farther into modern control theory, even for economics or econometric analysis. Computational intelligence is an area of active and vivid research, starting off with artificial neural networks. Pattern recognition. What patterns are there? How many different patterns can we identify in the forecast? And once we identify those patterns, how can we see how they will change and therefore add them back up to come up with the overall forecast? And of course, this can be done by genetic algorithms, where we look at certain drivers and look at how things can be changed. What's the optimal selection of components, and how do we add them back together? Evolutionary programming is an extension of that. Taboo search is another optimization technique to do the same thing, as well as other heuristic optimization methods. One thing I've noticed is everything is converging to state space or modern control theory. The student who is excellent in this area should be able to convert exponential smoothing, regression, principal component analysis, ARMA, ARIMA, seasonality into a state space framework and relate it to Kalman filtering, which is the ultimate state space filtering process. Of course, this is dealing with optimal control. And if you look at the books by Powell on control theory, he has some very good work in showing how ARMA and ARIMA can be converted into maximum likelihood estimates in the state space. In financial analysis, we have fantastic tools to use there in terms of qualitative, the market research of the Delphi. Why would this new Facebook idea take off and be a major user of consumer discretionary money? This is where we use the Delphi. Quantitative economic analysis is used by the Federal Reserve to establish the interest rates by using various indicators. GDP, that is gross domestic product, unemployment, cost of living, are all econometric type techniques that show us what's going to happen and therefore how far things are in balance or out of balance and what will the consumption be. In time series, we can do logarithmic, mean reversion, and of course we can use the higher order moments such as volatility, skew, and kurtosis to predict what the forecast in the future will be. What is the basic process? Well, first of all, you pick the problem to solve. You pick the data points to be used. You then use some kind of theoretical variables and an ideal data set to do the original work with. You have to identify the relevant variables, and you have to decide how to collect the data. Do you need to do a per house interview, if you will, as with some of the consumer price index type ad campaigns? That's about all I can think of them. What they are really is when you're part of one of these campaigns, you go home after you go to the store and you write down on your little device how much of this and that you bought, how many gallons of gasoline, where did you buy it, and then you allow it to call home and they gather the data by a certain sampling of the overpopulation. So you have to identify what kind of data is collected and therefore can be used for the forecast. You have to realize that you only have a finite time frame to look at. You can't model everything over all time because we just don't have the data. So you have to make a lot of assumptions. You choose a model, and you do this by experience and trial and error. And experience is really trial and error. So you pick a model that kind of fits because it looks like sinusoids, or it looks like exponentials, or it looks like natural logs, something like that. You pick a model. You then do the analysis using the model, analyze the data, and make a forecast. And you make a forecast of what has already happened. So you're forecasting the past based upon data farther in the past. That's the first step. because you want to see how well can you use historical data to produce the new data. And this is how you do verification or benchmarking. How do you forecast and compare the prediction to reality? And then you have to identify problems in terms of why is it not working. The problems. Data is always going to be old. Historical data is all we have to go on. The past is not predicted to reoccur always in the future, and historical data may have errors. It is impossible for economists or anyone to factor in unique or unexpected events, huge tornadoes, earthquakes, economic downturns, other things which we're going to consider externalities, the Chinese economy failing, and therefore we have more expensive goods to choose from. Assumptions are dangerous in any analysis, and most especially in the forecasting domain. It is assumptions that the banks were properly screening borrowing prior to the subprime meltdown. That was a very invalid assumption. So black swan events, which are what these are called, have become more common as their dependence on forecasts grow. The main thing you got to remember too is that forecasts can't integrate their own impact. If everybody starts forecasting the future better, that will change the future. So forecasts accurate or inaccurate, especially the accurate ones, will change the actions of businesses because businesses will plan their production based upon forecast. So this is an influencing variable that we really have a very hard time factoring in to the overall process. And this is a conceptual knot. In a worst case scenario, management becomes a slave to historical data and trends rather than the new business reality of what the customer wants and what technology changes have occurred. Bayesian methods are another group of techniques that have come forward for forecasting. They have not achieved a lot of acceptance in the electric energy business per se, but in other energy industries most certainly. They're very related to decision analysis and data mining, and they are dependent on degree of belief rather than historical frequencies of identical or similar events. So Bayesian methods allow us to fuzzify, if you will, for lack of a better word, the forecast so we can identify what the impact of the future will experience based upon the past. Bayesian methods use rules and assertions of the school of thought that pertains to frequency rather than subjectivity within Bayesian probability. Subjective Bayesian probability approach is related to the Delphi approach. Bayes Theorem, very simple, very controversial, called Bayes Theorem, Bayes Formula, or Bayes Rule, has always been contested as being unimportant in the past, but obviously is something that we use dramatically in many ventures today. This particular rule is most often used to calculate what is called the posterior probability, which is the conditional probability of a future uncertain event that is based upon relevant evidence relating to it historically. As new information or evidence is gained, one updates the probability of an event occurring. One uses Bayes' theorem to estimate the new probability. A very fascinating and extensive body of new work. If we do modeling Bayes' theorem, outcomes of historical data are used to base our beliefs from which we can derive new updated probabilities and therefore come up with a different forecast. Model results can be extrapolated to individual companies, given changes with their own balance sheets, the bond changes in credit rating for that company, customer dissatisfaction with the company, etc., to come up with a forecast of how their products will be consumed. So what if you have estimates but not exact probabilities? Okay, this is when you cross over into the Delphi system, and that becomes strongly into play. Many put faith in the estimates and simplified probabilities given by subject matter experts, called SMEs, SMEs, in their field, that they know what they are doing. The Delphi approach gives an ability to confidently produce new estimates for new and more complicated questions introduced by those inevitable roadblocks in financial forecasting. The whole idea here is that the past does not always predict the future and changes the future, and Bayes' theorem might be one way to handle this. Okay, so what about forecasting? This is still a ripe area for research and development. We still need to include technology changes. We still need to include regulatory changes. We still need to expand to include reliability standards, which is regulatory changes indirectly. Decision analysis and multivariate models with Monte Carlo analysis are very interesting at this point in time, especially to include fuel price uncertainties, such as the drop in oil prices and natural gas prices, as well as wind and hydro forecast errors and other probabilistic issues. One of the things